Hey everybody, welcome back to the Logarithmic Differentiation series. Yep, I ended the titration derivative series. Well, it's more of a mini-series because we're continuing the logarithmic differentiation. So, we're going to do some more of it here. We're going to do 3 examples, and I could totally do these as shorts, but I wanted to keep it all in one video, just because why not? So we're going to do some pretty basic examples, some very easy to work with functions. In the future, we're probably going to work with some more difficult functions, so let's just get started. Okay, derivative of x to the sine x. So let's first go through the wrong method of doing this. I'm sure you guys know what you're not supposed to do, but here is the wrong method, okay? That is bringing the sine x to the front and then subtracting by 1. So this is not equal to, okay, sine x times x to the sine x minus 1. This is not what you're supposed to do, okay? Do not do this. I'm gonna cross it off because we don't even, no. That's not what you're doing, okay? What you're going to do, you can actually do it in 2 main different ways. There are 2 different ways that you can do this. First is by using actual logarithmic differentiation, which I'm going to do for the rest of the video. But then the second method is a pretty nice little thing that you can also work with. Okay, so let's actually start with the way we're going to do this. We are going to let y equal to just x to the sine x, just our original function that we are differentiating. Okay, and y is a function of x. You can call it f of x if you want. It's up to you. And now we're going to take the derivative of both sides, because that's really what you do. If you have like f of x is equal to x to the sine x, to find f prime of x, you're really taking derivative of both sides, because derivative of f of x is f prime, and then you're actually finding the derivative of the other side. So let's do this. So derivative of this, I'm going to call it y prime, and this is going to be equal to, I'm sorry, no, we don't do this yet. We take the natural log of both sides. So we take, that's kind of the whole point of this. I don't know how I forgot that, but hey. Take natural log of y, and then you also take the natural log of x to the sine x. So natural log, I'm going to do it explicitly first. X to the sine x. Alright. And so from here, we will take, actually we can simplify this. That's the main reason we're using the log. By the way, you could use any log, but the natural log is the easiest to work with. So that's why we do it, because the natural log of this is just, well, you'll see it's y prime over y. I'm sorry, the derivative of the natural log. So logarithmic rules, we can bring the exponent to the front. So we can call this sine x multiplied by ln x. This is not sine of ln x, this is just these 2 things being multiplied. Now we take the derivative of both sides. What's this going to be? Y prime over y. Or you can think of it as 1 over y, so I'll just do 1 over y times y prime, whatever way you're more comfortable with. And then we're going to take, well, we have to use the product rule here. So we can write sine x as it is, and then take the derivative of ln x. That's going to give us sine x over x. So we can do that. Actually, let me write a little bigger so you guys can see that a little better. Okay, so now we're going to take the derivative of sine x, which is cos x, or cosine, and then we can multiply by a natural log. So we got cosine times the natural log. Okay, and then what we do is we multiply both sides by y, because we want to get rid of this. And what is y? Actually, I'll just do it explicitly first. So then we do this. Y prime is equal to y times sine x over x plus cos x ln x. Alright, so this is what we do. So, well, we can't have y's because we just made up y. Y wasn't even part of the original problem. So we have to replace our y's again with x to the sine x. So y prime equals x to the sine x, and then multiplied by everything on the inside. And you don't actually typically have to distribute with these kinds of problems, because it doesn't really make much sense to distribute it. With titration derivatives, we sometimes did, but it's really not necessary. Okay, well, what's the other method that I was talking about? So this is method A here. And then we got method B. Actually, let me use a red marker for that just to make sure you guys can see that. So we got A, that looks like a Q, A, and then we got method B here. All right, method B is pretty similar. We are just going to be using the rule that, I'm going to put it over here so I have enough space. Note that e to the ln x is equal to x. E to the natural log of x is equal to x. If you want to know why, basically they're inverses of each other. E to the x is the inverse of ln x. So if you take f of f inverse, you just come up with the identity, which is x in this case. Okay, so let's use that rule. So we can actually convert this into a form that is e to the ln of something. We don't even have to set up an equation or anything. We can just straight up go d dx here. Okay, well, we can write this as e to the natural log, right? And then we take our input, we put it in here, and it's just like these cancel out, and then it'll just become the original, and you'll see why. So this is x to the sine x. Let me make sure you guys can see that. So yeah, we used this rule, and then we plugged it in here, and boom. Okay, well, what's the purpose of this? Well, we can use the same rule with exponents that we did here, moving the exponent to the front, and we end up with, actually, I write better from this side, so I'm sorry if I'm blocking this a little, but, I mean, I can't do much. So this is going to be e to the, and then we move the sine x to the front, so we get sine x times ln x, and this result is going to be, I'm probably going to have to use 2 lines for the answer. It's going to be, let's see, so we got e to the sine x ln x, derivative of that is going to be itself, and then multiplied by, and I'm just going to use 2 lines again, that's going to be multiplied by the derivative of the inside, which we actually have right here, sine x over x, so sine x over x plus cosine times the natural log, right? And e to the sine x ln x is the same thing as this, right? It's literally copy-pasted, right? And this is the exact same as this, and this is just a rewritten form of that. So this first portion is really just this in disguise. And you can see that this is going to lead back to our original, or not our original, but our answer that we got using this method. So you can always use this method. This is a method I often use instead of writing out the whole y equals thing and then doing this. I like to do this because it's fewer steps, and once you know what you're doing, it's really easy. Okay, I'm going to give you 2 more, I'm going to do 2 more examples for you guys, and they should go by pretty quickly. Okay guys, so now we have the derivative of x to the ln x, which honestly isn't too bad again. We can just let y equal x to the ln x, right? And then all we got to do is move the, take the natural log of both sides, ln y is equal to, and then we remember the natural log is going to move to the front in the beginning, so ln x times the natural log of this x. So we get this ln x times ln x. I could write this as ln x squared, which I will actually, because that makes things easier. You could use the product rule. It's actually pretty easy either way. I'm just going to do it this way because it's pretty easy to use the chain rule. Okay, so we get y prime over y. And this is going to be equal to 2 times ln x times the derivative of the inside, which is x. So we got that 2 ln x, I'm sorry, that's 1 over x, so we're going to divide by x right there. Okay, and so now we just multiply by y, we get that y prime, or just dy dx, or really just the derivative of this, is equal to, well, what's y? That's x to the ln x, which, it's just x to ln x. So this is going to be x to the ln x times 2 ln x over x. And you can simplify this by saying this is x to the ln x minus 1 times 2 ln x. So I can give an alternate answer here, because this is x to the negative 1, really. So you can say this is x to the ln x minus 1 times 2, and you can move the 2 out front as well, which I'll do 2, so it's not really a great 2, as 2 x ln x minus 1 times an ln x. Alright, so these are both acceptable answers. And so yeah, okay, now we're going to move on to example 3, x to the e to the x. Alright, so again, we're just going to set y equal to x to the e to the x. Alright, now we're going to take the natural log of both sides. We got ln y equals e to the x times ln x. Don't like cancel anything out here. This is e to the x times ln x. This is taking your function times its inverse. That doesn't mean anything. It's not like you can simplify that in any way. The function composed with its inverse will simplify, but this does not. Well, not in every case, but you know. So this is going to give you the derivative of both sides. It's going to give you y prime over y. And then this, we have to use the product rule. So e to the x times its times ln x derivative is e to the x over x, plus the derivative of e to the x is just e to the x. So we can just say this is e to the x ln x, and then we get that y prime is equal to y, which is x to the e to the x to the e to the x times e to the x over x plus e to the x ln x. Alright, and again, you can you can distribute this and then do the minus 1. There isn't really much benefit to that unless you're trying to see something. And you can totally find anything like critical points here, which I'll go over in my AP Calc review at some point. And yeah, so you can, like, doing it this way is easy to find the critical points. Easier than if you distribute, because you can just see, well, x to the e to the x, when is that equal to 0, when is this equal to 0, and boom, you're done. So yeah, very interesting stuff. So yeah, these were pretty basic examples, and I know it's kind of weird coming off of like taking the derivative of the 6th iteration of x, but I just wanted to kind of reroute us, because it's been a long time since I've done some logarithmic differentiation other than our titration derivatives. So yeah, I just wanted to give you a refresher on how it's used, and in the next, whenever I make the next video, who knows whether that's like a month or 2 or 3 months from now, I don't know. We'll look into probably some more complicated examples. So yeah, thank you all for watching, and I'll see you in the next video. Bye guys.